Solving problems with more than one triangle. Can you see that we have more than one right-angled triangle in this situation? We have one of them that is XYW, and the other one which is WYZ. If you have a straight line and one of the angles is 90 degrees, do you know that the other one is 90 degrees? That the angles in a straight line always add up to 180 degrees. Calculate the length of XY. So what I'm going to do is draw a blue line from X to Y, because that's the length we want to calculate. Is that blue line part of a right-angled triangle? Yes. That blue line is part of XYZ. And if I draw XYZ just off to the side here, X, Y, not Z, XYW, sorry. It's part of triangle XYW. If I draw that off to the side and I label everything I know that this is 22 degrees. And if I wanted to do 180 minus 90 minus 22, I could tell that that bottom angle is 68 degrees. If you want to use SOHCAHTOA, you need to pick an angle. Okay? I have 68 degrees. Do I know an opposite side for 68 degrees? No. Do I know an adjacent side? No. Do I know a hypotenuse? No. And so the problem with these questions with more than one right-angled triangle is sometimes the thing that we want to find, XY, is part of a triangle, but we need at least one side in order to solve that whole triangle. In order to use SOHCAHTOA, we need one side. The angles aren't good enough, because we've learned with ratios, I can make a triangle with those angles small, or I could stretch it and make it bigger, and all the sides would change, but my angles would stay the same. So this type of question with more than one triangle, we have to say, hey, I might not have enough information to solve this triangle, but if I look at my other right-angled triangle, do I have an angle and a side? Yes. And once you have an angle and a side with that other triangle, you could solve for everything on that triangle. That was the section we did right before this, solving for everything in a triangle. You could find all the angles and all the sides. But now we're going to be strategic. In this WYZ, you have an angle, you have this, you could figure out the other angle, 70 degrees. You could use sine to find the opposite side. You could use cosine to find the adjacent side. But what we're going to do for a strategy is try to find what's going to be the piece of information on this triangle that's going to help us with that triangle. What should we find? YW. So can you see that this line right there, that's part of the triangle on the right, and it's part of the triangle on the left. So that red line, that's this one right here. If I redraw, and you don't have to do this much redrawing, but I hope this helps you visualize what's happening. If I redraw WYZ, this is 20 degrees. Could I use SOHCAHTOA to solve, and this is 8.4. I could use SOHCAHTOA in this one to solve for my red side. So this is where we have to know our definitions of SOHCAHTOA and find out which one we should use. Should we use sine, cosine, or tangent? We should use sine. We want to find for the 20 degrees. Can you see that this red side is opposite the 20 degrees and that The 8.4 is opposite the 90, so that will always be our hypotenuse. And one of the things you might want to do, if you like to label, like hypotenuse, you can just label all the time. But we have to be a little bit careful with opposite and adjacent because they can change depending on which angle we're using. So maybe a good thing for us for labeling is I'll write opposite, but I'll write the angle with it. So that's reminding myself, yes, that's opposite, but only opposite side for the 20 degrees. And now when I set things up, SOHCAHTOA definition, if I look back at it here, I have the hypotenuse, I want to find the opposite, I have the angle, so I have to use sine. So I write out my definition for sine. And I'll do this all in red because this is solving for the red side that we want. Sine of 20 degrees is the opposite side. So I'm going to call that WY, just because when you've got more than one label, we can't just call it a little letter. You could add a little x if you like that better. So if you like to add a little x here, then you could call it x. But for now, I'm going to call it WY divided by the hypotenuse, 8.4. How do I get WY by itself? Multiply both sides by 8.4. I have to switch my calculator back to degrees. In grade 12, you use radians all the time. So now we have 8.4 sine of 20, 2.87. My guess is we're going to need to use that number again, so I'm going to store it as x, just so that I have it stored for later. So I can go back to my original graph and say I figured this out to be 2.87. This is 2.87 there. That means this is 2.87 on that little graph. And now on that little graph, I have at least one side and an angle. Now I can solve for the blue side. Okay? For the blue side is my hypotenuse. And my red side, I'm going to, are you okay if I label that it's adjacent for the 22 degrees? For the 22 angle degree, the red side is the adjacent side. And now we can set up which is adjacent and hypotenuse. That's my cosine definition. So I can set up cos of 22 degrees is adjacent, which is the 2.87, divided by my hypotenuse. What letters do we have for hypotenuse? XY. So I'd multiply both sides by xy. And then divide both sides . So we need to type 2.87 divided by cos of 22. If we look back at our calculators, we're fortunate in that 2.87 was still there as our last answer. So probably the easiest thing that you would do in a situation like this is you would go second answer, because that's our answer, divided by cos of 22. 3.098. What are we supposed to round to? Read the question. Round to the nearest centimeter, tenth of a centimeter, 3.1 centimeters. So what we have is we have enough information in one triangle to find a key point of the other triangle. You have to, before you start solving things, decide what that key thing is going to be that's going to help you with the other triangle. And then from there, you can solve everything. And it's not always going to be just an opposite side. So let's look at our second example. The angle of elevation to the top of an apartment block from a window in a nearby apartment building is 28 degrees. The angle of depression from the window to the bottom of the apartment block is 34 degrees. The window is 24 feet off the ground. How tall is the apartment block? So we read a question like this, take a breath, and then we're going to have to read it again and try to draw a picture. So to try to get an idea of the whole thing in your mind, and then see if you can draw a picture of this. We have we're looking from one building to another building. So here is our one building with a window, and that window is 24 feet off the ground. And we have another building, the apartment block must be bigger, over here. The angle of elevation, looking from that window, the angle of elevation to the top, so here's a horizontal line, angle of elevation would make this 28 degrees. Angle of depression means you're looking straight out and then looking down. So your angle of depression right there would be 34 degrees. Can you see that this makes two right-angled triangles? If we know that the green line is 24, does it make sense that this line from here to here is 24 as well? We're asked to find how high the apartment building is. What do we still need to figure out? Yeah, this is the apartment building right here. This is the nearby building. If we already know this is 24, can you see that if we find out what x is there and add that to the 24, we'll be able to figure out the total height. If we look at the triangle where the x is in, that's this top triangle. Can you see that we don't know anything? Okay, I'm going to color code things here. We want to solve for this line here. That's my x. Can you see on the bottom triangle that we have an angle and we have a side? So we have two pieces of information. And if we have an angle and a side, we could solve that whole triangle. What side do we want to solve for? The adjacent side to the 34? I'm going to call that y. So when we're solving for more than one thing in a question, it's important that we don't label them with the same letter. I mean, you've solved for x before in algebra, and usually you solve for x, but when you have more than one thing in a question, you have to use different letters unless they actually equal each other. In this case, that red line is not looking like it equals the blue line. So we could solve for the y first. How can we solve for the y? If I redraw that triangle here, I know this is 24. I know this is 34 degrees. I know this is always my hypotenuse. This y is the adjacent side to the 34 degrees. If I write out my definitions, sine, cosine, tan, SOHCAHTOA, which one uses adjacent and hypotenuse? Close.
We need an adjacent and
Oh, right. That's right.
So we need
I was being sneaky there. This is the hypotenuse, but do we know the hypotenuse?
we don't need
No, we don't need the hypotenuse. We know this side here is the opposite of the 34 degrees. Right. So the side that we know is the opposite side, and the side that we want to find is the adjacent side. So we have to use tan. Set up our definition to start with. Tan of 34 degrees equals opposite 24 over adjacent, which is y. Whenever the y is in the denominator, you have to first multiply both sides by y, and then we would divide by tan of 34. How many of you are all ready just to multiply both sides and divide at the same time? Is that okay? Or is that too much work all at once? Okay? Is that too much work all at once if I do that in one step? So what have I done? What have I done? I'll do it in green here. I multiplied both sides by y. That moves the y over here and would cancel out the y's on this side. And then I divide both sides by tan of 34. And that, in effect, with a fraction, that just changes those two things. Have you ever played around with that with numbers? Did you know that that works with numbers? Right? Is 6 equal to 12 divided by 2? Yes. Right? Switch those two numbers. Is 2 equal to 12 divided by 6? It works. You can flip those numbers around on fractions. This is a powerful thing about algebra, because sometimes you notice things in algebra that you never thought about in real regular numbers. But everything that works in algebra works with regular numbers as well. And that can be very, very powerful if you start looking for patterns. Okay, but back to this. So now we can type this into our calculator. 24 divided by tan of 34, 35.6. And now that we've found the 35.6, I'm going to solve for x. I'm going to switch to the color blue. X is opposite the 28 degrees. The y that we know is adjacent the 28 degrees. Opposite and adjacent, we have to use our tan ratio again. So using blue now, tan of 28 degrees. Opposite side is the x, which I want to solve for. The adjacent side, which is the y, is my 35.6. Multiply both sides by 35.6. Oh, instead of writing 35.6, because that's rounded, I'm going to go second answer to steal that answer from before. multiplied by tan of 28. And we get x is 18.9. Take that 18.9. Another thing about the answer button. Okay? Right now, do you see I want to take this answer and add it to 24? So I could go second answer again, but your calculator knows if you pick any of the operation buttons, divide, multiply, add, or subtract, and you click that first, it'll automatically say, oh, you wanted to add that answer to what? Answer plus 24. 42.9. What do they want us to round to? Doesn't say, so we get to choose. 2 decimal places to live on the edge. Okay. 42.92. All right, let's look at your pictures. And again, for your pictures, it doesn't matter if you used the building. I'm going to draw the building here with the flag there. Oh, Canada flag. Very nice. And from a point 125 meters from the building, so I'm going to put that point here, and I know that this length is 125 meters. The angle of elevation to the top and bottom of the flagpole are 40 degrees and 37 degrees respectively. In English, when it says something respectively, that means that the 40 degrees goes with what was mentioned first, which was the top, and the 37 degrees goes with what was mentioned second, which is the bottom. So to the bottom of the flagpole, this angle of elevation is 37 degrees, and to the top of the flagpole, and here we have to be careful, the 40 degrees isn't this little part in between. The 40 degrees is an angle of elevation, so it always starts at the horizontal going up. So it might have been that you drew your 125 degrees to the left. Some of you drew 125 degrees to the right. They're both perfect. It doesn't matter which direction you drew. How many of you had your 125 degrees on your left? Okay. How many people had the 125 degrees going to the right? Okay. So it's about half and half. Perfect. The ideas in the math is all going to be the same. Okay. What is the height of the building? So I'm going to say this is one of the things that we want to find out. I'm going to call that x. What is the height of the flagpole? I'm going to call that y. Can you see where our 90-degree angle is? My next question is, how many triangles do you see? 3. Some people see 2. Some people see 3. The question is, can you see 2 right-angled triangles? This top little triangle, is it a right-angled triangle? No. So we won't be able to do any math with that triangle. Not yet. Not until next semester. Oh, I know, anticipation. Can't wait for trig for next semester now. No, we can't use that triangle, but can you see the second right-angled triangle if you don't use that one. The big one that goes all the way along the bottom, all the way to the top of the flagpole and down. Okay? So I'm going to redraw both of my triangles. Okay? This is how I'm going to redraw them. I can cheat. You can't. I can just trace it out perfectly and take one of them and put it over there. And can you see that the other one is right like that? These are both 90 degrees. Let's label what we know on these triangles. This angle on the big one is 40 degrees. This angle on the smaller one was 37 degrees. We know that it's 125 on both of them. So unlike the questions we've done so far, on both of these right angled triangles, we can solve for everything. Okay? What are the things we want to solve for? We want to solve for x. Oh, my green x, that would be this side over there. Well, I can do that right away. But I also want to solve for y. And can you see that y is not on any of those two triangles? In fact, the y was only this little part from there to the top. So how am I going to do that? You can solve for the whole thing. Can I introduce another letter? What do you want to call this whole thing? What letter do you want to use? Z. Z? Okay. If we call that whole letter Z, I'm going to pick a new color for Z. That whole letter Z, that would mean on this triangle, this is the whole letter Z. And the letter Z is equal to the side of x plus the side of y. So the suggestion is that we solve for all of z, and if we solve for x, we could just subtract x from z, and we'd figure out what y is. But we have some work to do. Let's do the green x first. If I'm solving for the green x, the green x is opposite the 37 degrees. The black side that we know is adjacent to 37 degrees. So from our definitions of SOHCAHTOA, which one uses the opposite and the adjacent? Tan. So we write out our definition. Tan of 37 degrees will be opposite side divided by adjacent. Multiply both sides by 125. $94.19. Switch colors to purple. We're going to solve for Z. Again, it's going to be very similar because on Z, this is the opposite side of the 40 degrees, and this is the adjacent side of the 40 degrees. Opposite and adjacent, we need to use tan again. So now tan of 40 degrees will equal Z over 125. Multiply both sides by 125. Take out our calculator. I'm going to show you something on your calculator. Can you see that what I want to type in is the exact same thing as before, except instead of 3740? Above your enter button is the word entry. If you push your entry button, it will retype what you typed last time. If you keep pushing it, it will keep going up and doing the one previous. So now I can just go to where the 37 is and retype 40 over top. I don't know how much faster that is. Maybe a tiny little bit. But it's just interesting. So typing it in, we get 104.89. I maybe should have stored some of my answers, especially if you have an older version of calculator. Once we solved for x, you might have liked to store that as x, and then the other one stored as z. How do we solve for y? We'll have to go z minus x. So I can take my answer, 104 minus. Now, if I had stored it as x, I could just type in x. On the newer calculators, you can go up and highlight something, and it retypes it for you, which is also very handy. And we get y is equal to 10.7. It's a word problem, so we should write a statement. Does it tell us what we need to round to? No, so you get to choose. Okay? But it says find the height of the building and the height of the flagpole. I'll round to the nearest tenth. But we were given units, so we should have our units in our answer. The height of the building is 94.2 meters, and the height of the flagpole is 10.7. So this one, the two triangles, was a little bit different. It was harder to see both of the triangles because one was hidden inside of the other one. And this time we didn't need to solve for a piece of information to help us figure out the next one, but we had to use information to subtract to find the height of that flagpole. So the last one we're going to do today is this one. A helicopter directly above a highway spots a car moving away from it at an angle of depression of 27 degrees. 5 seconds later, it's seen at an angle of depression of 25 degrees. Helicopter's 1,000 meters above the ground. So, draw our helicopter. Ooh, that looks like an airplane. The drawing, right? Oh, yeah. Whew, I like that helicopter. So there's our helicopter. It is 1,000 meters above the ground. And angle of depression. So we draw a horizontal line out from here. It says at first the angle of depression to the car is 27 degrees. Not a very nice looking car, but that's okay. And then 5 seconds later, the new angle of depression is 25 degrees. There's our right angle triangle. Can you see that this is another case of one right angle triangle inside of the other one? The other thing we have to look at in this case is that our angles of depression are not actually labeled inside of our triangle. Right? The 25 degrees is not inside of any of the triangles. The 27 degrees is not inside any of the triangles. How far did the car travel in 5 seconds? So we want to find this length here in blue. I'm going to call that x. Notice that the length x is not part of any right angle triangle. So what's helpful in these cases, and what we did last time, is we took both of our right angle triangles. Here is one right angle triangle. We take it, we redraw it, put it down there. And our second right angle triangle is the big one. So I'm going to take that one, redraw it, and put it over here. We know that this is 1,000 meters on both of them. And with the first right angle triangle, we have to use the fact that that angle of depression is 27 degrees to help us label angles inside of the triangle. And in the second one, we have to use the fact that the angle of depression is 25 degrees to help us draw this triangle, to label angles in that triangle. So if I know this is 27 degrees, how did I figure out that this angle here is 63 degrees? Yes. This makes a 90-degree angle here, so these two have to add up to 90. An interesting fact, so over here, this one's going to be 65 degrees. An interesting thing about angles of depression, if you add up all these angles to make 180, this angle of elevation down here is 27 degrees. This angle of elevation down here is 25 degrees. And that will always happen, that that angle of depression and that angle of elevation will be equal. So looking at those triangles, we have angles, we have a side, we could solve all of that triangle. But what do I want to find? The distances that, so here in green, I'm going to label that as y. And here on this one in purple, I'm going to label that one as z. I'm going to color code this back on my original picture just so we know what's happening. Can you see that the green is that distance and that the purple is that whole distance? So I'm going to introduce another letter for that. I'm going to go z. Okay? And what do we know about z? So this question is very similar to the last one that we did. Z is equal to the x plus the y. As you get better on these, okay, there's sometimes an angle which is maybe a little bit easier to work with. In this case, if I think about SOHCAHTOA, and tan is opposite over adjacent, it's always a little bit harder if the thing that you're trying to find is the adjacent side because it's in the denominator. Not always the case, but it's often a little bit harder. So if I want what I want to solve for to be the opposite side, in this one, I'm going to use the 63 degrees. So for the green one, I'm going to say tan of 63 degrees, because then my y is opposite of 63 degrees, and my 1,000 is adjacent to 63 degrees. And tan of 63 degrees is opposite, which is the one I don't know, y, over my adjacent, which is 1,000. I can get y by itself, multiply both sides by 1,000. $1962.6. This time I'm going to store it, store alpha y, so that I remember that 1962 is y. 1962.6. And in purple now, I can do the same thing. Z is opposite 65 degrees. The 1,000 is adjacent 65 degrees. And so tan of 65 degrees is opposite over adjacent. Multiply both sides by 1,000. And Z is 2144.5. On my calculator, I'm going to store that answer, alpha Z. Again, color coding, making your notes really neat and clear is going to be important because now we're getting into questions that have more data points, more things that we have to work with. So often we have to go back and still look and say, have we solved this question? Are we done? And if we're not done, how is my work nicely organized so that I can figure out what I want to find? We were asked in this question to find out how far the car moved. How far did it travel in 5 seconds? This car goes from here to here. That's that x. What do we know? We know the whole thing, and we know y. So x will be z, the whole thing, minus y. So I can go back to my calculator. I've stored all of these things in, so I can go alpha z minus alpha y. What is z minus y? 181.9.
Did you check if it stores it every time that you...
Oh, yeah, we should check the letter that we had from yesterday. Okay? Now I forgot the number. The car traveled 181.9. Did it ask us a certain rounding? Traveled 181.9 meters in 5 seconds. I'm going to store that as x. That was my answer for x. What letter did we use yesterday? G? Still remembers it. But I don't know if I've shut it down. Should I close it? Oh, but I don't want, okay, I don't want to close it yet. So this car traveled 181.9 meters in 5 seconds. If I multiply 5 by 12, 5 times 12 is 60. So then I can take x times 12. This is how many meters it traveled in a minute. If I divide that by 1,000, that's how many kilometers it traveled in a minute. If we multiply that by 60, 60 minutes an hour, that's how many kilometers this car would travel in an hour. 130.9 kilometers per hour. Should the police helicopter give this car a speeding ticket? Yes, if he can catch him. Or, right, just deliver the speeding ticket with one of its rockets. Maybe not a good idea.